In this experiment, I'm going to talk about inverting operational amplifiers. So the first thing that you need to know is that you need to learn about the data sheet that has been provided in this link. So this amplifier has 8 pins. You are going to use only pin 1, 2, 3 and 8. You're not going to use 5, 6 and 7. This op-amp needs the two supply voltages. The positive one, which is here, is going to be positive 5, and this one is going to be negative 5. This is the minimum voltage that this op-amp accepts, and because this the software and the analog discovery tool only provide the maximum of positive 5 and negative 5, we are going to use these values. This is the output of the op-amp, which here is this node, and this is the negative input, and this is the positive input of this op-amp. Here is a negative input and here is the positive input. So I'm going to construct this circuit on the board, and for now there's nothing else to mention here. Which means these values I need to connect R4, R3, R1 and R2, and I need to ground this positive input. As you can see here, R4 is a 10K resistor, so I need a 10K resistor. This is a 10K resistor. Okay, I will put it between, I need to put it between the output and negative input, and according to the datasheet it's between pin 1 and pin 2. So it's going to be here, between this one and this one. And then we have, so I've connected this one, R4 10K between the output and negative input. Then I have R3, which is 1K going from negative input to somewhere on the breadboard. We call it node B. So I need a 1K resistor, and I need to put it between the negative input and somewhere on the breadboard. Okay. Then according to this circuit, from that node B that we just built, we need to put 100 ohm resistor to ground. So I'm going to choose one raw as ground. Okay, so I'm going to connect this 100 here, and I'm going to choose, for example, this row here as ground. Okay, and then according to this, we need to have another resistor R1, which is 10K from that node that we called it B, to somewhere which our input is going to be injected into. So the R1 is 10K. I'm going to take a 10K, put it one pin here, and one pin is going to be for the input. Okay, so this needs to be grounded for the 100. This one needs to be connected to the input, and this node is the connection of this tree, which is node B. Okay, There is one other connection left, which is the positive input of the op-amp, which needs to be grounded too. So I'm going to use a wire and connect these two nodes, which means here, and the positive input of the op-amp. I need to see which node is positive. The third pin of the op-amp is the positive input. Okay, so I'm going to ground the third pin, which is going to be here. Okay, now our circuit is complete. So there are a few connections remaining, two of which are the ground connections, which are these two black wires that you can see here, and you can find them on the paper that is for analog discovery 2, and here I connected two grounds, so these two are going to the ground. Then now I have 3 voltages available on the breadboard. One of them is this voltage, which is -5. One of them is this voltage, which is +5, and one of them is 0, which is these nodes that are connected together here. For the input, I'm going to inject 5 volts, so you need to do 0 and -5 volt yourself. I'm going to use the 5 volts on this circuit here and inject it to the input. So I need to connect this here. Next time when you want to, for example, do part A, now I'm going part B. Next time when you want to do part B, you need to connect this. When you want to do part A, you need to connect this to this row, which gives you 0. Next time you need to connect it to this row, which gives you -5. Okay, I'm going to do only one part. So this is done. Now to measure the value, the value of the output, we need to have the connections of the oscilloscope. So I just connect the negative of the oscilloscope to this ground node. There is one pin remaining here. And then I'm going to use the other wire of the oscilloscope to do the measurements. So I need to see node out, which is according to the data sheet is pin 1. I need to see node B, which is here, and here is the connection of this tree, and I need to see the node C. Node C is going to be 0 all the time because it's in the negative feedback and your op-amp has a high gain, so it's almost always going to be something around 0, node C, which no matter what input values you have, your node C is always going to be 0. So I'm going to do the measurements. For example, when I want to measure the output, I'm going to put this wire in the first row somewhere here. Sorry. Okay. So you can see it's connected to the first node. I'm going to move to the waveform software and show you what settings you need to have. Uh, I need to insist once again that you need to make these two connections properly. If you do not connect these two, I mean positive VCC and negative VCC correctly, you will damage the op amp and even it can burn. So please make sure that the connections for these two are correct before turning on the power supplies. So I'm going to move to the waveform software. I'm going to use the supplies. One of them is going to be positive 5, the positive supply, and the negative supply is going to be negative 5. Okay. I haven't run the supplies yet. I need to open the voltmeter. Okay, and now I will run the supplies and run the voltmeter, and you can see the DC value of the output here. Now that we saw the output of the op amp and the circuit that we built for positive 5 volts, I want to see node B, the voltage of node B for this input value. So I'm going to remove the wire from output node and connect it to the node that we have the connection of this tree, which is node B. And then I'm going to run the waveform software once again. So I'm going to once again run the supplies and run the voltmeter, and you can see that DC value of node B is 47 or 48 millivolts. The next part of the experiment is asking you to shunt a 4 resistor with another resistor with equal value, which means that you need to put another R4 here in parallel with the R4 that is still existing in your circuit. So R4 is 10K. I'm going to put another 10K in parallel with this R4 that exists in my circuit. So as I mentioned, in this part you need to put another 10K resistor in parallel to the 10K resistor which already existed in your circuit. So you just need to put one of the pins here and the other pin here. The next step is asking you to put another resistor in parallel with R3. So you just get rid of this one. You first do the measurements for the circuit that you have with this R4 in parallel with the existing R4. I mean V out, VB and VC. You do the measurements, then you take out this resistor and you put another you put another 1K in parallel with this 1K resistor, and you do the measurements. The next step is asking you to open the connection for of R3 at node B and add a resistor in series with that, which means that you need to open this resistor here, this 1K here, put it somewhere else on your circuit like this, okay, and then from there you need to add another 1K and connect it to your circuit. So you need to connect a resistor from here to that previous node, node B. Okay, so as you can see, our tree is in series with another R3. R3 is in series with another R3, and it goes to the same node B. Then you do the measurements V out, VB, and VC, and you move to the next step. And you need to measure the voltage at this node too, the connection of these two 1K resistors. The next part of the question, meaning 3.3, is asking you to remove whatever you added to your circuit in part 3.2 and return the circuit to what it looked like in figure 1. And then you need to inject an AC signal to your input instead of the 5 volt DC that you 5 volt DC that you injected into the signal in part 3.2. So it means that I'm going to remove this wire from here, because I was using this as an input, and I need to use the waveform generator, which, as you know, is this wire, the yellow one here, and connect it to the input, and the input is here. Okay, so I can now, in this waveform software, I can inject an AC signal with the wanted values and see the output. So as I mentioned, in this step we are going to inject a 5 volt peak and 1 kilohertz sine wave into our circuit. It's necessary that you keep in mind that this op-amp, in order to work, it needs its supplies to be connected. For example, this one here, this pin 8 and this pin 4 needs to be connected to positive 5 and negative 5. So moving to the waveform workspace, the supplies need to be connected to positive 5 volt and negative 5 volt and both be activated. The wave generator needs to provide a sine wave that is 1 kilohertz and has amplitude of 5 volts. And then you need the oscilloscope. Then you run the supplies, you run the waveform generator, and you run the oscilloscope. You press on single, and you can see that the output voltage for this circuit is 0.9 almost. And then I'm going to move this, first I'm going to stop everything, and then I'm going to move the output wire of the oscilloscope to node B, because I want to show you that the values will change. So turn on the supply, turn on the waveform generator, and turn on the oscilloscope. You see that the peak to peak is now 90 millivolts. Now I'm going to again stop all of this and move the wire on the circuit to node C, which was node C, which was 3, because it was the I'm sorry, node it was 2 on the op-amp. Okay, pin 2 on the op-amp. So I'm moving the wire on the circuit that we have built from node B to the negative, which is the second, and again I'm I run the supply, I run the waveform generator, and I run the oscilloscope. And you can see that this node has a very small value, as I've mentioned in previous steps. You don't need to do part B and C because these parts, for example, part B needs to have an amplitude higher than 5 volts to see the saturation, but unfortunately analog discovery doesn't provide higher than 5 volts, and you don't need to do part C again because you don't have the analog discovery won't give you the precision that you need to measure the offset.